We're going to go ahead and do a few more examples with cyclic groups, and then we're going to look at the primitive root theorem for this week's asynchronous work. So let us remember from last class that we say that the set generated by an element is the set of all powers of that element, which really just means that we're doing the group operation repeated times with that element and then looking at everything that we get out. And we say that a group is a cyclic group if we can find some element that when we look at the set generated by that element, we get the entire group itself back. So what we saw in class was we saw that all of the groups Zn are cyclic groups because we could always find a generator. And let's just kind of do a little bit of practice with that. So if I look at the group Z16, we remember that our operation is addition mod 16. So if I want to list the elements in this set generated by the element 4, I'm going to have 4 itself, and then I'm going to have 4 plus 4, which is 8. And then I'm going to have 4 plus 4 plus 4, that's 12. And then 4 plus 4 plus 4 plus 4, that's 16, but we're working mod 16, so that's actually 0. Once I get back to 0, which is the identity here, I'm going to just be stuck with these same elements again because if you notice, I'm just adding 4 to the previous element to get to the next one. So if I add 4 to 0, I get back to 4, and then I'll get back to 8 and then 12. So these are my 4 elements here. We notice that this is not equal to Z16 itself. So 4 is not a generator of Z16. Okay. And then if we look at the elements in the set generated by 3, we're going to have 3. 3 plus 3 is 6. 3 plus 3 plus 3 is 9. And notice again, to get from one element to the next, I'm just adding 3, which is the thing that we started out with. So if I add 3 to 9, I get 12. 3 to 12, I get 15. Then I get 18, which mod 16 is just 2. I add 3 to that, I get 5. I add 3, I get 8. I add 3, I get 11. Then I get 14. I add 3 again, and I get 17, which gets me back to 1 because I'm working mod 16. And then I add 3, I get 4. I add 3, I get 7. I add 3, I get 10. 13. Now I get to 16, which is 0. If I add 3 to 0, I get back to 3. So then I'll just be stuck looping around. So I get all these out. Notice that this contains all the numbers from 0 to 15. So this is all of Z16. That tells us that 3 is a generator for Z16 because starting with the element 3, I can add 3 to itself multiple times to get all of Z16. And if you remember from class, all of the generators of Z16, these are going to be the numbers that are relatively prime to 16, so the numbers that share no common factors with 16. 16 is just 2 to the 4th, is that right? Yes. And so the generators of Z16 are going to be the numbers that have no 2's in them or not divisible by 2. So 1 would be a generator of Z16. 2 is not because it shares a 2 with Z16 or with 16. 3 is. 4 is not because it has multiples of 2 in it. 5 is. 6 is not. We're not going to notice that in this case, we're going to have all the odd numbers. So 7, 9, 11, 13. 15 and not 17 because we're working Z16. We only have numbers smaller than 16. So we get these numbers out. So if I looked at the set, for instance, generated by 5, I would get all of Z16 out. That's what it's saying to be a generator. Okay. So then again, if we look at all the generators for Z28, these are going to be the numbers that have no common factors with 28. So 28, if I factor that, that's 4 times 7, which is 2 squared times 7. So I'm going to look for all numbers from 1 to 27, or from 0 to 27, really, that have no common factors with 28. So that have no 2's in them and no 7's in them as factors. So I can include 1. I can't include 2 because it has a factor of 2. I can include 3. I can't include 4. I can include 5. I can't include 7 because it shares a 7 with 27. I can't include 8. I'm not going to be able to include any even numbers here because this has a multiple of 2 in it. So 9, I can include 9. I can't include 10. I can include 11, 13, 15, 17, 19, 21. I cannot include because it's divisible by 7 also. 23 is good, 25 is good, and 27 is good. Okay, so these would be the generators of Z28. Okay. So let's look at some groups that are not ZN and just kind of get a feel of how cyclic groups work in those cases. So this is our fun group. This is that group of colors that we saw on the first day of class. This is the Cayley table for that group, and I want to know if this group is cyclic. So I want to know if there's one color that will generate all of the other colors by this color mixing that we have here. This is kind of interesting. So the thing that we would want to do is like, well, let's just start out by picking a color and look at the set generated by that color. So let's look at the set generated by black. So when I'm looking at the Cayley table here, we're going to definitely include the color black. And then I'm going to say, what happens when I add black to itself? What do I get? Oh, I get black. If I add black to itself 3 times, I'm still just going to get black back. So the only element in this set generated by the color black is just going to be black itself. Okay? Black was the identity in this case. The identity, the set generated by an identity element is always just going to have the identity in it. Okay, let's try. So this is definitely not a generator because that was not the whole set or the whole group. So let's look at the set generated by red. Okay, so it's just certainly going to have red in it. And then it's going to have red with red. So red paired with red gives me black. So it's going to have black in there. And then it's going to have red plus red plus red. But red plus red, let's see. Red plus red plus red. Well, the red plus red was a black. And if I add black and red, I'm going to get red back. So this is going to be red again. So I'm going to be back to the element I started out with. So these are the only 2 things in this set. Okay. And then you might want to try this for some of the other ones, but it's going to turn out that like if we look at the set generated by blue, that's just going to end up being blue and black again. And that's because blue added to itself gives black. And this is going to turn out to be the case for any of these colors, is that there's only going to be 2 things in the set generated by that color. It's going to be the color itself and black. And so none of these are generators for the group itself because we don't get all of the other colors back by starting out with a single color. So that means that this group is not cyclic. Okay, I can't start out with one color and mix it to itself multiple times to get all the other colors, which kind of makes sense because if I mix red together a bunch, it doesn't make sense that I should get like blue back. Okay, so we're going to look at a few other examples here. So let's look at our dihedral group. So remember, these were the symmetries of different shapes. And so if I'm looking at D3, these were the symmetries of a triangle. R was just our rotation by 120 degrees. And so if I look at the things in this set generated by R, I have R itself. Then I have rotate by 120. Then I have, R. So that's rotate by 120, rotate by 120 again. That's the same thing as rotating by 240, and we called that R squared last time. And then if I look at R, that's 3 rotations by 120 degrees. That's just a rotation by 360, which just gets us back to where we started. That's just the identity. Okay. And then if I do 4 Rs, that's going to get me back just to R because that's a rotation by 420, which is the same thing as 420 might not be right, 480, which is the same thing as rotation by 120. Okay, once we get to the identity, we're done. So these are the things in this set generated by a rotation, is that I just get all the other rotations. Okay, sorry, I got my little brackets backwards. So remember F1, that was a flip through kind of the top vertex. I flip my triangle through that vertex. So the things in the set generated by F1 would be F1 itself. But if I flip through that vertex and then I flip through that vertex again, I get back where I started. So I get the identity now. And once I get to the identity, I'm stopped. Okay. Similarly, F2 will just have F2 and the identity. F3 will just have F3 in the identity. Okay, so what we're noticing here is that these reflections, the flips, the things in the set generated by a flip are just the flip and the identity. The things in a set generated by a rotation are just going to be the other rotations. And so what this tells us is that D3 is not cyclic. I can't just start out with a single rotation and get all of the elements in D3. I can't start with a single flip and get all the things in D3. Okay? So we're seeing some good examples of cyclic groups and not cyclic groups. So if we look at all of the integers, we want to know if that's cyclic. We remember that this is a group with multiplication, or not with multiplication, sorry, with addition. Silly me. So this is an additive group. So I have to ask myself, is there any integer that I can add to itself multiple times to get to any other integer? And you might think that 1 would work. So it is. So yes, it's cyclic. It's generated by 1 because if I think about adding 1 to itself multiple times, I'm going to get all the other integers. I have to also include inverses. So the thing that we haven't really done in this notation up here is that this notation also means include negative exponents, which means include the inverses. We haven't had to do that yet, but we're also going to include all the inverses. So as soon as I include -1 in the set, I'm going to get all my negative numbers as well. So this is going to give me all the integers back. I can also use -1. So -1 and 1 are my generators here. Okay. The set of real numbers is also an additive group. Remember, the real numbers were the things of the form a over b, all of our fractions. This is not a cyclic group because I can't think of one fraction that if I add itself to itself multiple times or subtract, then I'm going to get all the other real numbers, all the other fractions. So I can't start with one fraction and get every other fraction out. So integers with addition is a cyclic group, real numbers are not. Okay. In the next video, we'll do the primitive root theorem, which is going to tell us about a very specific type of group and when it's cyclic.